Today we want to talk about the last part of our lesson, conservative and non-conservative forces. Conservative forces, like what? Force of gravity, force of spring, these are examples of conservative forces. Okay, what does it mean? When we have a conservative force, the total mechanical energy in a system remains constant. It means, you remember what does it mean mechanical energy? Mechanical energy is the sum of kinetic and potential energy. So all the time, at the beginning, in the middle, at the end of the motion, total mechanical energy stays the same. It means that if kinetic energy increases, for example, by 2, gravitational potential energy will decrease by 2. If kinetic energy increases by 5, gravitational potential energy will decrease by 5 because they will leave or they will keep the total mechanical energy constant. Okay, let's watch this simulation together to understand exactly the meaning of conservative forces.
If we hit play and we watch the skater go back and forth, we can also look at a graph to see what's actually happening here. So I'm going to put on this bar graph. And if I drag the bar graph over to the side, what we can see is that the total energy of the system remains constant. And we see that the energy itself is in two forms. It's potential and kinetic that are continually fluctuating back and forth. We notice that if I hit pause at the top, that the energy is in the form of potential with very little kinetic. And that's because potential energy is based off height, and we do have a height compared to this particular spot. The kinetic energy is in essence 0 because he's at the top and he's stopped moving, and at this point is when he turns around to come back. If we hit play and pause at the bottom, we see that the kinetic energy is boosted up because now he's at his fastest speed, which has come at the expense of the potential energy that he once had because he has very little height left. Now, this is because gravity is a conservative force. A conservative force is one that will behave this way. When a conservative force is present, the energy will just switch between kinetic and potential energy, keeping the total energy always constant.
Okay, let me explain to you what happened here in this case. Now here, we will assume that this surface has no friction. We don't have friction here in this surface. It is a smooth surface, zero friction. No friction, no air resistance. We are in an ideal system without friction, without air resistance, okay? What is the only force that causes this motion? Force of gravity. So, we at the top here, what we will have? Maximum gravitational potential energy and zero kinetic energy. While it starts to go toward down, what will happen here? Gravitational potential energy starts to decrease and kinetic energy starts to increase with the same rate. At the end, the total energy stays what? The same. The total energy here, and for example, if the total energy here is 10 joule, while it's going toward down, kinetic energy, for example, it becomes, here it was 0, it becomes 2, gravitational potential energy, it will become 8. Okay? This is the meaning of total mechanical energy stays constant. At the bottom here, what do we have only? We have only kinetic energy. We have 0 gravitational. So the kinetic energy here will be what? 10 joules. It equals the total mechanical energy because gravitational potential energy is 0. So no energy lost to the surrounding because there is no friction in this case. All of the energy is kinetic and potential mechanical energy. Okay, so when we have force of gravity or spring, in this case, we are talking about conservative forces. Total mechanical energy stays constant and equals what? You remember the sum of kinetic and potential energy. Here we are going to use something we call it law of conservation of energy. Energy before equals energy final. Energy initial equals energy final. So kinetic energy initial plus gravitational potential energy initial equals kinetic energy final plus gravitational potential energy final. What's this formula? It is mechanical energy initial equals mechanical energy final. Here, that's it. And we know that mechanical energy is kinetic plus potential, sometimes gravitational, sometimes elastic potential energy. Clear? So, in any question, we have force of gravity, force of spring without friction. How do we solve the question? We use this formula. Kinetic energy initial plus gravitational potential energy initial equals kinetic energy final plus potential energy final. Here we have some examples. I will solve them with you after I finish explaining non-conservative forces. Now the second type is non-conservative forces. For sure now you know examples for non-conservative forces. Force of friction, air resistance. In this case, the total mechanical energy is not conserved, is not constant. When energy is gained by the system, the energy comes from the environment. When energy is lost by the system, the energy moves to the environment. What does it mean? Let's watch this video, then I will explain to you.
Put a little bit more friction in this time. Looks like it slid down. So if we check our graph now, we see that as he moves, the thermal energy is continuing to increase, while these two still are fluctuating, but they're going down and down and down. Notice that his motion on the other side is slowing down and slowing down and slowing down. That basically means that he is losing this energy in its mechanical form. Now, the law of conservation of energy is valid, but just not the way we've been using it in this chapter. If we look over on the side, the total energy is still constant. It's just turning into an alternative form that we are not addressing in this chapter. So when we identify that there is a force present beside a conservative force, that would be friction, thrust, or any other force, pretty much it's not gravity that can perform work, we need to use the work-energy theorem. When the energy, or when the force is only coming from gravity, instead we will use the law of conservation of energy. I hope.
So, now in this case, we have friction. The surface is what? Is rough, is not smooth. And we have friction. So some of the energy, some of the kinetic and potential energy is lost to the surrounding. Okay? As what? As heat. Because of friction. So now total mechanical energy is not conserved, is not constant, but total energy. Now girls, energy, we have mechanical, non-mechanical. Now the total energy is conserved because the energy transferred from kinetic and potential to non-mechanical, like what? Thermal, heat. And also thermal is an energy, but it is what? It is not mechanical, it is non-mechanical energy. But the mechanical energy here, kinetic and potential, they are not equal. Okay? The total mechanical energy is not constant at the beginning, in the middle, at the end, because some of the energy is lost to the surrounding because of friction, because of non-conservative force like friction. The transfer of energy into and out of a system is known as the work of non-conservative forces. So we have work here from non-conservative forces. It is equal to the change in energy of the system. So work of non-conservative forces equals the change of energy. Yes, for sure. We have work here of friction. It is because of the change of energy in the system between kinetic, potential, and friction. Kinetic friction, it's an example for non-conservative force. Kinetic friction acts on moving objects such as the roller coaster. When kinetic friction acts, some of the total mechanical energy of the system is lost. Listen that. Some of the mechanical girls. You can say that total energy. Total mechanical, yes. It will lost to what? To non-mechanical, like what? Friction. Kinetic friction transfers a portion of the initial energy to the environment as heat. We said that. As a result, the final kinetic energy and the speed are less than they would have been in a frictionless environment. In the first case, when there was no friction, the initial energy and the final energy here at the top, here and here, the two sides, is what? The initial energy and the final energy here, they are equal. Okay? But in the case of friction, they are not equal. And for example, if he starts here, he cannot reach the same point here. He will reach a point less height than the first point because some of the energy lost while he's moving in this case of friction. In the first case, there was no friction, no, he will continue moving without stopping because the energy is not lost. We have energy. Here you saw in this example, because of friction, at the end he stopped here because he lost all his energy to the surrounding as a friction. The decrease in kinetic energy when kinetic friction slows a moving object is referred to as kinetic energy loss. The work done by kinetic friction is equal to the product of the force of kinetic friction and displacement. So, if I ask you to find the work done by friction, how do you find it? You multiply, you remember force of friction, mu k, coefficient of kinetic friction, times normal force. This is the formula for force of friction. Times what here? The work, force times distance. And now we know the formula for work is force times distance. Here I want to find the work done by friction, by a non-conservative force. So what is the force of friction? We know the formula of it. And displacement, we multiply it by the displacement. The work done by friction is equal to the kinetic energy lost by the system and the resulting heat transfer to the environment. Sometimes, girls, they don't ask you to find work of friction. They say the question, find the kinetic energy lost. Okay, how do you find it? We don't have a formula for kinetic energy lost, but it equals the work of friction. So you find the work of friction. This answer equals the kinetic energy lost by the system or heat gained by the environment. Okay, that's all for our lesson. Also, we have this example. I will solve it with you now in another video in an external paper.